Hello, everyone. In this video, we are going to discuss vectors. Vectors. Consider a 3D space and two distinct points in this space. A vector is the directed line segment from an initial point to a terminal point. One way to write a vector is to represent it in terms of its initial and terminal points. A vector is a quantity that comprises both magnitude, which is also called its length or norm of the vector, can be 0 or a positive number, and direction, which is denoted by its direction angles. Direction angles will be a topic in another video. In contrast, a scalar is a quantity that is just a number or magnitude and does not have direction. Component form of a vector. A vector can also be expressed as an ordered triple, where each number is called a component. The first number is the x component. The second number is the y component. The third number is the z component. Each component can be positive, 0, or negative. 3 components make up a vector in space, while only 2 components make up a vector in a plane. Note the use of angle brackets to denote vectors, while the use of parentheses to refer to a point. If an initial point and a terminal point are given, then the component form of the vector is given by the following expression. Each component of the vector refers to the difference between the corresponding coordinates of the terminal point and the initial point. In the figure, the initial and terminal points are defined by their own x, y, and z coordinates. From these coordinates, each component of the vector refers to the length of the vector along the x, y, and z directions. Position vector. Aside from its coordinates, another way to describe the location of a point is through its position vector. A position vector is the vector formed from the origin to the point of interest. For points P and Q, these are the position vectors. Note that point O is the origin 0, 0, 0. So subtracting its coordinates from point P and Q will result to these position vectors. Thus, the vector formed from P to Q is equal to the position vector of Q minus the position vector of P. Which is a similar result from the previous page using the initial and terminal points. Equality of vectors. Suppose we have two vectors u and v. They are equal if and only if the x components are equal, the y components are equal, and the z components are equal. Thus, u and v are equal if they have the same magnitude and direction. Referring to vector v in the figure, a vector u is equal to v if it is the exact same vector. Or vector u could be another vector with a different initial and terminal points but must have the same magnitude and direction as vector v. Meanwhile, opposite vectors are non-zero vectors with equal magnitude but opposite direction. Two vectors are opposite if the coordinates of one vector are the negative of the coordinates of the other vector. Two non-zero vectors are parallel if they have the same or opposite direction regardless whether their magnitudes are equal or not. Norm of a vector. The norm or magnitude of a vector is its length, and it is the square root of the sum of the squares of the components. If an initial point and a terminal point are given, then the norm of a vector is given by the following formula. It is a scalar quantity, which means it has only a magnitude or a number, and it does not provide information about direction. For vector v in the figure, its norm or magnitude is the same as the distance between the initial and terminal points. Hence, the formula for norm is the same as the distance formula. Note that for the norm or distance, the quantities inside the parenthesis can be the coordinate of the terminal point minus the coordinate of the initial point or vice versa. Now, let us talk about some properties of the norm of a vector. Scalar multiple. The norm of a scalar multiple of a vector is the absolute value of the scalar times the norm of the vector. The vector kv is k times every component of vector v. Note that k is any scalar, negative, 0, or positive. The norm of kv is given by the square root of the sum of the squares of its components. Factor out k squared. The square root of a squared quantity is the absolute value of that quantity, and the remaining quantity inside the square root is the norm of v. Hence, the norm of kv is the absolute value of k times the norm of v. Unit vector. A unit vector is any vector whose norm is equal to 1. It can take any direction, but the norm stays at 1. Note that the vector 1, 1, 1 is not a unit vector because its length is actually equal to the square root of 3. Zero vector. The norm of a zero vector is equal to 0. The vector 0, 0, 0 is the zero vector because its length is equal to 0, and it has an indeterminate direction. Arithmetic operations on vectors. Sum. The sum of u and v is equal to the sum of their corresponding components. The sum of two vectors can be illustrated by arranging the two vectors one after the other. The sum of these two vectors is the vector from the initial point of the first vector to the terminal point of the second vector. Similarly, for three or more vectors, the sum is the vector formed from the initial point of the first vector to the terminal point of the last vector. Difference. The difference of u and v is equal to the difference of their corresponding components. The difference of two vectors can be illustrated by arranging the two vectors such that their initial points coincide. The difference of these two vectors is the vector formed from the terminal point of the subtrahend to the terminal point of the minuend. If we want to subtract two or more vectors, we can first add them all up, and then subtract from the first vector. Note that u and v are vectors of any finite magnitude, so u does not just refer to unit vectors. Scalar multiple. A scalar times a vector is the same as multiplying each vector component by the scalar. For a vector v, vector kv is the vector where each component is multiplied by k. The absolute value of the scalar determines the length of the scalar multiple. If the absolute value of k is greater than 1, the vector becomes longer. If the absolute value of k is equal to 1, the vector is unchanged. If the absolute value of k is greater than 0 but less than 1, the vector becomes shorter. And if k is just 0, the result becomes the zero vector. Meanwhile, the sign of the scalar determines the direction of the scalar multiple. If k is positive, the direction remains the same. If k is negative, the direction is reversed. In both cases, the vector and its scalar multiple are parallel vectors. And if k is 0, the result is the zero vector. Properties of vectors. Commutative. The order in which the vectors are added yield the same vector. However, when multiplying vectors, the commutative property may or may not hold. For dot or scalar product, the product of two vectors is commutative. Meanwhile, for cross or vector product, the product of two vectors is not commutative. Vector multiplication will be discussed in more detail in another video. Additive identity. A vector plus the zero vector is the vector itself. Additive inverse. A vector plus its negative is the zero vector. Multiplicative identity. A vector multiplied by a scalar 1 is the vector itself. Distributive over addition of scalars. A vector is distributive over a sum of scalars. Distributive over addition of vectors. A scalar is distributive over a sum of vectors. Vector multiplication is also distributive over addition. The dot or scalar product. And the cross or vector product. Associative. The grouping a sum of vectors does not change its sum. Another associative property. The grouping of the product of scalars and a vector does not change its product. Vector multiplication also has associative property. The dot or scalar product. And the cross or vector product. Unit vectors. A unit vector is a vector with a length of 1. Normalized vectors. Suppose V is a vector in space. A normalized vector V bar is a unit vector with the same direction as the vector V. And it is the vector V divided by the norm of vector V. In the figure, V bar is the normalized vector V. It has magnitude of 1 and it points to the same direction as vector V. Standard basis vectors. These are reference vectors used to write a vector in a linear combination form. I, j, and k are unit vectors along the x, y, and z axes, respectively. I has a component of 1 along the positive x-axis. J has a component of 1 along the positive y-axis. K has a component of 1 along the positive z-axis. These unit vectors have 0 components along the other two axes. A vector can be expressed as a linear combination of the standard unit vectors I, j, and k. That is, vector v is v1i plus v2j plus v3k. Let us illustrate the meaning of writing a vector as a linear combination. Consider a vector in space. Let's start with the initial point P. v1i is this vector parallel to the x-axis. And then, v2j is this vector parallel to the y-axis. And then, v3k is this vector parallel to the z-axis. Finally, we end at the terminal point Q of vector v. This is the principle of adding vectors, as discussed earlier, where the vectors are put one after the other, and the sum is the vector formed from the first initial point to the last terminal point. Summary of vector notations. Two-point form. A vector is a directed line segment from an initial point to a terminal point. Meanwhile, a vector can be written in terms of its components. A component is the length of the projection of the vector onto an axis. Ordered triple form. A vector is an ordered triple where the first number is the x component, the second number is the y component, and the third number is the z component. Each vector component refers to the difference of the corresponding coordinates of the terminal point and the initial point. Linear combination form. Using the standard unit vectors I, j, and k, a vector can be written as a linear combination of its components. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.